Stop share. All right. Okay. Now, Martijn will start off.
Yeah. Okay, guys. So welcome to our presentation. We are very excited to share with you our model or our project on modeling grid cells. Of course, my name is Martijn and my partner's name is Tim, and we'll be accompanied during this presentation by our small friend, Jerry. He's a mouse and he will help us understand the grid cell models that we will talk through. But before we start, I will give a brief overview of what we're going to discuss. First, we'll have a refresher on what grid cells are. After that, we'll look at some nice visuals which will get you an intuitive understanding of how grid cells work. After that, we'll look into the models that currently exist for grid cells, and then the fun part comes, which will be our own model for grid cells. And finally, we will check back up on how Jerry's doing. So what do we already know about grid cells? Well, I think all of us have seen this grid card before, or this flashcard. Grid cells are cells in the entorhinal cortex that are involved in coding for space. And the interesting thing about grid cells is that they have multiple firing locations. And these locations are determined by an hexagonal grid. And the interesting part is that this hexagonal grid, this regular grid, is completely determined by the nervous system of an animal. So independent of the outside world. So there's some very interesting internalization happening here. Now, Tim will talk us through the visuals that will get you an understanding of how they work.
So basically, we have a nice little video here. And what you can see is we attach an electrode to Jerry, and we're just going to record the firing of a single grid cell of Jerry as he moves around in this enclosure. But what's interesting here is if we go to the end here, that you see Jerry running around, the grid cell firing gives a nice grid-like pattern. And this is important because this is what we want to see later on in the model, see if we can achieve this single grid cell response in our computer model. Well, another good idea of how this all works is here we have a nice little block which shows a grid with 16 grid cells. And basically, as we let this little red dot move around, you see at the bottom left which grid cell corresponds to the firing of that movement. And this kind of gives an idea of how these grid cells can show where you're currently at, because every movement corresponds to a different grid cell of that designated area. Now, Martijn will talk about a couple of models we can use to implement this grid cell working.
Yes, so keep in mind that if we want to have a grid cell model, it should recreate the same patterns that we've just seen in the visuals. And as a first step to find a model, we looked into academic papers, and we found that there are two general models for grid cells. The first one being the oscillatory interference model, and the second one, the attractor network model. And we've explored both of them. But for the discussion, we'd like to focus on the attractor network model. And we have two good reasons for this network. So we can use the knowledge that we've learned in this course on neurodynamics and apply it to this network. And secondly, because it's a network, it's programmable. And that's what we, of course, love to do as econometricians. So before we get into our own code, I'll firstly briefly explain how the attractor network model works in general. So in this network, there are many grid cells, and grid cells that are close to, or that have firing fields that are close to each other, they excite each other, while grid cells that have firing fields that are far away from each other, they inhibit each other. And this setup of nearby excitation and far away inhibition, it leads to the generation of attractor sites in this network, which are called bumps. And the exact location of these bumps for each grid cell is determined by the input into the network. And for the case of grid cells, that is the information about the heading direction of the animal and velocity. So to sum it all up, the attractor network model integrates inputs about the heading of an animal to determine where exactly the spikes of a grid cell are going to be. And now Tim will take us through our own model.
So what we did, we considered two different models for attractor network model, which were laid out in the paper by Burek and Fiete. And there are two distinctions for this attractor network model. We have the periodic model and the aperiodic model. And basically the difference between these two models is that here you can see this is the network population of many different neurons. In the periodic model, the boundaries are well defined and have strong firing. And then in the aperiodic boundary, at the boundaries, the grid cells or these blobs you see disappear and they reappear at the other side again. Well, the reason we're going to focus on the periodic model in our paper now is because this aperiodic model only works with proper fine-tuning. And even with proper fine-tuning, generally does not perform as well as a periodic model. So to take a look at the input and output of our model, I'll show you the nice little MATLAB code we were working with. What we do here is here we have the code for our data. We tried to look for data of real mouse movements, but couldn't find any. So we just took this code.
I have it. Okay.
Oh, yeah. Oh man, yeah. We asked Elias, but Elias said he couldn't. They have a resource for us.
Yeah, I have it from a master thesis. Sorry, continue.
Oh man. So what we did, we created here was random data, and we kind of just influenced this random data to our own likes. So if we plug in some data we have here, we plug in this the positions of the mouse and the direction he's heading, and we get this nice little visual of our grid cell firing. So it starts off with initializing the neural population network here. If you give it a moment, we'll start to see the movements of our mouse. Just creating the network. So it takes a little while. Yes, there it's going. And now you can see here, this little red dot is our Jerry running around. And basically whenever he crosses a certain area within this grid, a grid cell will fire. And this corresponds to the neural population activity here above. And you see this neural population activity moves in the direction of Jerry movements. So it doesn't completely follow his movements, but it kind of floats towards the movements where Jerry's moving around. And here you see the first blob of grid cell movements. Well, to test the accuracy of this model, we put it in a couple of parameters. I'll go to the right one. And we focus on 3 parameters. Focus on 3 parameters for this presentation. And what we want to show is how network size influences the model, how Jerry's movements influences the model, and how the amount of noise can influence the model, which Martijn will explain later. Well, to show the accuracy of a model, what we want to see is the grid cell-like pattern, which we saw in the video at the beginning. Because in the paper of Fiak and Burak, the equivalent condition for the accuracy of the model is this grid cell response of the single neuron. So here we see 16 neurons by 16 neurons. Here's the neural population activity. We see this poor grid-like, not a very nice clear grid. But when we increase the number of neurons, we see the model is more accurate, and we can better represent where Jerry's moving around because we see this better grid-like pattern here. Well, when we focus on the velocity and closure, so we focused on how quickly Jerry is moving and how big of an enclosure affects it. Basically what we see here, Jerry is moving around very, very fast. He's looking at the edges of his enclosure, and we see we can not distinguish any grid-like pattern at all. And you see the neural populations are going crazy. They're starting to blob together, activating very highly. But we see here, if we increase the number of neurons and we increase the size of the enclosure, the neural population is still going crazy, but we see a little bit more of the grid-like pattern which we want to see. Well, now Martijn will explain a little about noise with a nice little graph we created.
Yes, so thank you, Tim. We created code to implement noise into this model. And noise is the introduction of discrete spiking events. And these spiking events are stochastic, and this stochastic nature induces a lot of variability into the model, which would also induce drift. And drift is the difference between the actual and the modeled location of the firing locations of the grid cells. And in the paper that we got this code from, the authors propose a model for the drift at any given time. So as you can see, we've visualized it here. The drift is given on the vertical axis, and it's a function of V, which is the variability, and the number of neurons, which is displayed as X. Now, as you can see, as Tim is shifting the variability, if we increase the variability, the function shifts upwards. So we would expect the drift to increase. However, we can also observe that as the number of neurons decreases, this drift decreases again. So based on this information, this tiny model, we would expect to see a less accurate model if we introduce noise, but we would expect this effect to decrease again if we increase the number of neurons. So now Tim is going to show if this was actually the case.
So here we included noise into the model. And basically what you can kind of see what the noise does, we see not a nice clear grid-like patterns in our neural population activity. They're all uneven, they're not as equally spaced as before. And this is a high level noise with a network that is 64 by 64 neurons. What we see here, when we increase the number of neurons, we still get the same level of noise that we saw before in the model. So we were not able to achieve the result of decrease of drift in our model, because you can still see here, this one's completely disappearing, some are very strong and appearing, and they're all completely uneven. So that's something we would have to take another look at. Well, now off to Martijn to finish off our presentation.
Yes, so what have we learned in our project? Well, we've learned many things. We've dived a little bit deeper into grid cells. We've looked at some nice visual representations of grid cells. We've discussed 2 models of them. For this presentation, of course, only one in a little bit more depth. From our own model for grid cells, the attractor network model, we've learned that the accuracy increases with the network size, but decreases with velocity for a given enclosure space. And the effect of noise is a little bit ambiguous on the accuracy of the model. So the big question is, has Jerry actually paid close attention and learned how he can get his food? Tim will show it to us. It looks like he has, and he's a happy mouse now. I hope all of you listeners are as well.
Learning.
Thank you for listening.
Thank you.
Thank you, Martijn. Thank you, Tim. That was quite nice. I didn't get it. Was it a spiking model?
Sorry?
Was it a spiking model?
Yes, I think so. Yeah.
Now, basically, what you see with the code, that they made a distinction, but they just measured the firing of the neural network. Here, I'll move this away. I'll pause it and quit debugging. They basically measured the activity of the neural network, and what they wanted to do is they included spiking and as an option. So basically, we see here we can add spiking, and it adds neuron decay with these random spiking events. And basically, what it does.
Okay, so
yeah.
Got it. Interesting. So basically, spiking is modeled inside the network. It's not a direct spiking mechanism from the grid cells, but it is a source of perturbation to their encoding. Question number 2. Where do the grid cells, so how do the weight from the head direction cells and velocity cells get encoded into the grid cells? Basically, what's the weight matrix from the inputs to the network?
Well, there's 2 differences. I can probably better show you in the paper what was considered. You're right here. Well, basically, the difference is between the aperiodic and the periodic model, and that decides the weights which are chosen. And we see here all the way at the bottom, basically for a periodic network with the strong boundaries, we use an envelope function with 1 everywhere. And for the aperiodic network, they made the difference between the location of the grid cell.
So where's the head direction? Where's the velocity?
So this R is basically the diameter of the network, so how large the network is. The delta R is basically more of the direction and the place where it is. So in the middle of our network, if the mouse is more in the middle of that network population above, at a strong weighting function, and at the edges, the weighting decreased.
Okay, so basically it is a topographical set of findings. There's nothing learned here. It is assumed that grid cells receive from head direction cells and velocity cells from different places.
Yeah, basically. That's kind of the reason why the aperiodic performed a little bit worse, because of the inclusion of this envelope function that we used. And otherwise, the normal weight function was just here, the current weight matrix based on the current location, with the direction of the A is represented the head direction of the mouse.
Very good. Questions from the crowd potentially? I mean, like, you use the chat, okay? So like, I'm just then gonna relay the questions to the presenters. Next group can already come on in. So we have the full